Good evening. I'm delighted to see a virtual, almost full house tonight. It's great to see so many of you, and I see a lot of new faces in the audience. I really appreciate that. My name is Leslie Gordon, and I welcome you to the U.S. Geological Survey in Menlo Park in another installment of our continuing monthly public lecture series. As usual, I have announcements, and before I introduce tonight's speaker. Late tonight, there's a full moon. It's actually full at 3:45 in the morning tomorrow. And it's a blue moon. And people know what a blue moon is? It's the second full moon in a calendar month. So tonight we'll have a blue moon. On that theme, what does that have to do with anything? I'm going to apologize in advance for the warm, stuffy air in this room. It's a nice, warm summer evening in California, and we do not have control over the air conditioning in this room. We've already tried. It's so modern that everything is programmed in advance, and nobody can just walk up to a thermostat and fix it. This is technology in progress, and there's a lot of warm bodies in this room. So I apologize. We've got the doors open. If the glare is too much, let me know, but it's a choice of the glare or fresh air. All right. Because I always want you to come back next month, it's unusual. We're going to have 2 earthquake talks back-to-back, which is unusual. We'll be talking about earthquakes tonight. Next month, we'll be talking about man-made or human-caused earthquakes, or what we call induced seismicity. So do join us next month on August 27th. Justin Rubinstein will be talking about human-caused or induced earthquakes and seismicity and all the questions that I see in the news all the time. So please do join us again next month. Tonight, we're going to take a little historical tour, and I promise you will enjoy this. Brian Atwater is a research geologist with the U.S. Geological Survey. He is in our Seattle office, so we're very fortunate that he was able to travel to California and be with us today. He started his career here in Menlo Park in 1974, but has been in our Seattle office since 1985. Brian uses coastal geology, in other words, looking at the rocks and the sand and the mud, to learn about earthquake and tsunami hazards. And he has contributed to basic discoveries about earthquake hazards in Washington State, in Chile, Japan, Thailand, and the British Virgin Islands. He's also been involved with publishing fact sheets and booklets for laymen, some public safety booklets about tsunamis in Chile, Indonesia, and Pakistan, all with the purpose of saving more lives. Early in his career here in California, he surveyed remnant marshes in San Francisco Bay in the estuary, and he mapped the geology of the Sacramento and San Joaquin River deltas. Brian Atwater is a member of the National Academy of Sciences. He is a fellow of the American Geophysical Union, and in addition to being on the USGS payroll, he's an affiliate professor at the University of Washington, and we're really lucky to have Brian Atwater with us here tonight. Thank you.
How about that? Okay. Well, thank you, Leslie. Thank you all for being here. This is from a public safety brochure in Tanabe, in an area near Kobe, Japan. And you have an observant cat and a human, and a subduction zone. You can see the downgoing plate there going into what's labeled in the square characters up above as a torofu or something like that. So it's a trough, a trench. And And there are two more of these, and what they capture in some ways is the theme of tonight's talk, which is the use of the ups and downs that take place at subduction zones as a way of learning about the earthquake and tsunami histories at these places. In the Japanese case, they have a long written history. In the case of the area we'll talk about tonight, the northwest of the United States, essentially written history begins with Lewis and Clark, but the Earth operates on cycles longer than with subduction zones. It can operate on cycles much longer than the mere 200 or so years, and so it's useful to use geology to extend history farther back and to learn about hazards that you wouldn't otherwise know about. So our observant cat here is a geodesist looking at the deformation. This is not a real geophysically realistic picture. You'll see a more realistic one, but you can see the idea that some part of the leading edge of the overriding plate is getting dragged down. What's also happening to that plate is that it's getting shoved in. The left-hand side is getting shortened, right? And so really the coast should be bulging upward, and that will play out later on. But in the final shot here, the top line of text says, it says in Japanese, earthquake and tsunami. And you think about the March 2011 disaster in Japan with the very large loss of life in northeast Japan. But you compare that loss of life with the number of people who are in the places that got wet. And the estimates I've read on that are that 95% of the people who are in the places who got wet, they survived. Okay? And so it's sometimes thought that tsunamis just can't be survived, you know. And despite the problems that Japan had with that disaster, they had surely an aware population with people who'd been schooled in the kind of simple message that's in these cartoons, that if you feel an earthquake, get yourself to high ground. And so that probably contributed to quite a bit of life-saving in Japan. But that depends on an understanding, fundamentally an understanding that you have that hazard in the first place. And so that's where we're headed with this talk, is sleuthing back in the past to learn about hazards that wrote themselves into geological history, but too early to show up in written history in northwestern North America. However, not too early to show up in written history in Japan. So we're going to see a trans-Pacific detective story. So too early for the northwest of the U.S. So this map was made for the King of France. Some of you may know of a New Yorker article that came out that contains a memorable quote about how everything west of Interstate 5 is toast. I live 5 blocks west of I-5, so I kind of wondered about that. And then I thought, well, maybe, you know, the French map maker knew about this all along. But I-5 doesn't go that far east. But it's remarkable that, okay, 1720, let's see. They didn't know about San Francisco Bay then, did they? Right? But Cape Blanco, they'd already been up as far as Cape Blanco and Cape Mendocino. So that's, I think, Cabrillo, and then there's somebody later than him in 1600. Who is it? Vizcaíno. Thank you. He goes on to Japan and does things there. So speaking of Spanish things, okay. So we've got to backtrack a little bit here to learn about some of the pioneers in land level change related to earthquakes. And probably the earliest one on record is Maria Graham. And if you go to this lovely old home north of Valparaiso in Chile, a museum for a This guy, Thomas Cochrane, was a mercenary who founded the Chilean Navy. You can read about Maria Graham in Spanish. Some of you can get the general idea that there was some intelligence involved. The dotes, I think, means gifts, that she had exceptional gifts to write. And she was doing that at the time of Chile's independence or just after it. And that if you're Chilean, you can discover on her pages of her diary that she had a sharp vision of to tell, maybe, I don't know, with a profound analysis, a psychological analysis of our early heroes, that may mean Thomas Cochrane, among others. But she was an astute observer of nature, and this led to a discovery and got her in some trouble, and she gave at least as good as she got in that. So she wrote a diary, a published journal, really, a book about her time in Chile, published 2 years after she got back, after she was in Chile. And this is her self-portrait in the book. She's the person on your right in the coach. But she also maybe communicated or was asked to communicate an excerpt from that journal about what she saw in relation to an earthquake in 1822. And so here's what she says about it. It appeared the morning of the 20th. The earthquake happened on the 19th of November 1822. That the whole line of the coast from north to south, a distance of above 100 miles, had been raised above its former level. And she gives a bunch of evidence for it, and this is one of them. When I went to examine the coast, although it was high water, so it was high tide, I found the ancient bed of the sea lay bare and dry. She means just the day before bare and dry, with beds of oysters, mussels, and other shells adhering to the rocks on which they grew, the fish being all dead and exhaling a most offensive effluvia. And she went on to identify raised beaches along the shore as well. She was an astute geological observer. Well, this got her in trouble with a guy named Greenough, who thought that the only way that a coast can, or any part of the Earth's surface can get raised is by means of a volcano. And 10 years later, 10 years after she published this, he attacked her in her most unpleasant way in an address when he was the president of the Geological Society of London or something like this. And the backstory is that Greenough was having a long-running battle with a guy named Charles, right? Lyell, who was the first geology textbook, really, is by Lyell. And Lyell had cited Maria Graham and said, you know, that earthquakes can be associated with the raising of coasts. And this was anathema to Greenough, but rather than attack his adversary, Lyell, he went after what he thought was the weaker target. And he made a mistake. So her rebuttal, which is just this marvelous thing, you can go online and find this. Just Google Maria Graham and Greenough or something. Anyway, she says, this is part of, just a small excerpt. Mrs. Calcott, she'd gotten remarried. There were some losses of husbands along the way. Had read with surprise in the Athenaeum of June 14th an extract from Mr. Greenough's anniversary address to your society, in which there is an uncourteous attack upon her letter, addressed to Mr. Warburton, the letter that's up there at the beginning, in the year 1824, giving an account of the earthquake, blah-de-da. Okay, and so she writes this in the third person. It's marvelous. Mrs. Calcott, and she has a lot of stuff she defends and just sort of levels him, but one of her points is, you know, I was seeing the facts. I wasn't deluded. Even though I am a woman, I am capable of observing facts. And so she says, Mrs. Calcott had ample means and leisure to observe the coast at Quinterno and Valparaiso, places distant from each other 30 miles. And she saw the difference between the old high water marks on the cliffs, beach, and rocks from 3 to 4 feet higher than the new high water ever reached during the 2 months she remained in Chile after the first great shock. And then she goes on, because she knows that Greenough's having this battle with Lyell, and she's positioning herself. She's a very savvy geologist, but she's saying, and I'm not really a geologist. She says, she is indifferent whether Mr. Greenough ascribes this to partial elevation of the coast of Chile or to a change in level of the whole mighty Pacific Ocean, which must have extended to Polynesia, India, and China. The fact is that there was a change. The fact is, right, that there was a change in the relative position of the land and water. And to save circumlocution, Mrs. Calcott will continue to use the word raised or elevated in describing that change. Yeah? So she really lets him have it. But it's well worth reading the whole thing. It's an amazing exchange. So she does this. If you go, Darwin eventually goes and stays at the home of Thomas Cochrane. And Darwin cites Mrs. Graham, right? But soon, with Darwin and Fitzroy, that became the official establishment of the fact that earthquakes can be associated with the raising of coasts. But really, Maria Graham got it first. Okay, this person, this is another going back. So now we're up in the United States. Cooper was born in New York. He went to medical school at the College of Physicians and Surgeons. He got his MD at age 21. I guess that was common in those days. He practiced medicine for 2 years in New York, but his real wish was to be a naturalist, as his father had been. And an opportunity came up when the then Secretary of War, Jefferson Davis, pushed forward an initiative to have surveys made of several, I think 3 different railway routes, potential railway routes to the Pacific coast. And he wrote to the Secretary of the Smithsonian Institution, who knew of his father's work, and he said, I'd really like to be a naturalist on one of these railway surveys. And that Smithsonian person landed him a job on the railway survey of Isaac Stevens, the northernmost one, which involved Cooper's going down through Panama and up to San Francisco, then changing boats again and taking a boat up to Fort Vancouver in what's now Washington, where he met a lieutenant named Ulysses Grant. And then his supervisor on the survey was a captain named George McClellan. So did I pronounce him correctly? But the Civil War general. And when he went back to D.C. to write the report that's written at the bottom, he dined with Robert E. Lee. So really sort of interesting background. But the railway survey didn't occupy him very long, but the Smithsonian was willing to support him to stay there, and they sent him out to the Pacific coast of Washington to a place that was then called Shoalwater Bay, shallow water, now called Willapa Bay. And Cooper was particularly struck by, he was there studying the botany, and he was struck by a tree, western red cedar, that's particularly durable, and he wanted to give 2 examples of the durability of the wood. And he gave the familiar one where you have a fallen tree of this species lying on the floor of the forest, and then some great big old growth trees that had used it as a nurse log, and the wood is still good in the downed log, right? So that was his first example. Second example, on some of the tide meadows about Shoalwater Bay, dead trees of this species only are standing, sometimes in groves, whose age must be immense, though impossible to tell accurately. So he's saying tide meadows. He means like salt marshes, you know, like Palo Alto Baylands and stuff. They evidently lived and grew when the surface was above high water level, and so on. And he eventually says, continued and careful examination of such trees may afford important information as to the changes of level on these shores. So he's channeling Maria Graham a little bit on these. And the trees are indifferent as to whether the sea rose or the land dropped, but there were some changes in level. So that's Cooper. There's one other person here. Many of you know this person's work, but you know the place here. Is it Bolinas Lagoon? Does that look like it? And the photographer, Grove Carl Gilbert. And so Pepper Island is the place that a place that Gilbert visited at Bolinas when he was surveying the rupture of the 1906 San Francisco earthquake. There's a little side note on Gilbert about, you know, he came out here to do work related to hydraulic mining debris, and he starts off in Sacramento, and he's not happy there. And there's a correspondence in July 1905. I've been 2 months in the state with headquarters at Sacramento, which place I find so dull that I've downslidden to billiards in a public billiard room. If I spend the winter here, the base will probably be shifted to Berkeley, where there are people I like to know. So he did go to Berkeley, and then the earthquake happened. And at Berkeley, he met Willis Jepson. And Jepson, those of you who have used old botany books here would know that the first California flora before the sort of more recent ones is Jepson's flora. And he has Jepson standing out here along the fault. And can you see the trace of the fault in this black and white photo? So it's the tonal difference. Jepson's standing on the side of the fault where the land didn't drop. And then he's looking across to the place where there's standing water and the pickleweed's not very happy. And that pickleweed marsh proceeded to die. And so in this way, Gilbert was tuned in. So you could think in the earthquake story that I'm going to tell you, the pickleweed are essentially Cooper's trees. Okay? Okay? The land drops, and the vegetation can't take the inundation by the tidewater. Okay, in the room tonight is George Plafker, I believe, standing here, and George is in a Maria Graham kind of moment here. He's standing on an area that was raised in Alaska during the earthquake in 1964. And the pattern that George and his coworkers mapped out is this very big pattern of some areas being raised and some lowered. And my understanding from George is that the expectation when they went to do a post-earthquake survey was they might have something like the San Andreas Fault and a crack in the ground, and they'd map it and they'd be done. And instead, they found that they had to map out all those shores, and the more they mapped out, the more that they saw, more widespread they saw the land level change was. And they couldn't explain it by having a little vertical fault just sitting in there. They had to have a very gently inclined fault. And this was subduction in action at a time when the term plate tectonics didn't even exist in the scientific literature. So this work in Alaska and subsequent work in Chile with a similar earthquake there these were very, very important in the development of the idea of plate tectonics. And it's it's not easy to frame the question of whether there are big earthquakes in the Pacific Northwest without plate tectonics as that guide. The portage is labeled. Montague Island is where George was standing, the big white dot out there in the raised area. And then near Anchorage, Portage, a garage that went for a swim with high tides in the summer. And the spruce trees also got put out of commission by the tide. So the garage is also Cooper's trees, if you will, okay, or Gilbert's pickleweed. So it's that idea. So now you're getting the sense of how an earthquake can write its own record ecologically. You know? That you can change the landscape by making garage owners and trees uncomfortable, right? So also what comes in with that is up there at Portage is you have these giant tides. It's a 10-meter tide range up there, 30 feet. And the tides come in charged with enough sand and silt that in the months after the 1964 earthquake, the land was down at the level, the brown stuff is the soil from 1964, and then the tides built all this stuff up above. And each of those layers probably represents an individual high tide. And you know the way that there are, since it's a blue moon, there are tides, the tides would be extreme at this point. And then you get partway through when the tides would be less extreme. So you can see down here a time when the tides were less extreme. And then the extreme tides give you the very thick layers here. So just a couple of months in the summer of 64 probably that you built up a fair amount. The shovel here is the same style as the one on the screen. So this helps you because if you have a tree trunk or a willow or even a pickleweed that's rooted in the soil there, the sediment builds up around it and it preserves it, right? So you get an archive. So in the big picture view, this poor series of kind of stark cartoons, you have a subduction zone like the one with the Japanese cat, only we've flipped it to be a North American view rather than a Japanese view where the plate goes in the other direction, the subduction goes in the other direction. And the part of the fault that's stuck is shaded with the heavy brown line, and the two tectonic plates are moving towards one another. And there are some trees living dangerously close to the shore. And in between times, between the earthquakes, the land gets bulged up because that plate gets shorter as things get squeezed here. And with that spring loaded, as in the Japanese cartoon, then the tsunami takes off once the earthquake gives you the slip that lets the leading edge of the plate flip up, and some parts behind get stretched out so the land drops. So where you see it, so Maria Graham's shorelines were in place, and George's were in places where you have the upward arrow, and then the Portage example would be one with down dropping. The San Andreas is a slightly different case. It's not this tectonic setting. And the tsunami takes off in both directions, right? So there's a part of the tsunami that's heading towards your nearby coast, and that's the dicey one because that gives you that's where the cat cartoon comes in for the public education in Japan. The Association of Earthquake and Tsunami don't wait for the government to tell you what to do. Just treat the earthquake as a natural warning because the tsunami arrived very quickly. And then there's another part of the tsunami that's heading across the ocean, and that'll take some time. But finally, the poor tree, because the land has dropped, ends up in an uncomfortable spot here in the tidewater. So that was there's a lot of groundwork that was laid for this. The parts of the Cascadia story I'll try to mention here, many scientists from different fields, especially geophysics, in framing the problem to begin with and working on some evidence for the vertical and horizontal movements of the land in the Pacific Northwest during the 20th century. But still there existed into the early 1980s, after plate tectonics had been coined and the existence of the fault been recognized and the activity of the fault had been confirmed by seismologists, they didn't know whether it made big earthquakes like the one in Alaska in 1964, right? And so these were the two possibilities, and there was some thought that there's a lot of wet sediment that gets dragged down along the fault and that the water pressure would just allow it to slip in a benign fashion. So for the generic Portland and Seattle, the cities sitting over there in the cutaway view, this was a question. So the map on the left projects to the Earth's surface the patch that's shaded in the lower diagram, okay? It's the part of the fault where the fault breaks. And we're talking about very big earthquakes where epicenter doesn't really cover it. For a lot of earthquakes, you put a dot on the map, and the area where the fault broke is covered by that dot. In a case like this, the fault might decide to start to break here or there, wherever it is along there. That's going to, in plan view, that's going to be your epicenter. But what really counts is what length and width of the fault breaks, and that's what's going to give the seismic energy and the tsunami to follow. So you could see that. You could see that here, that the displacement on the fault is what's driving the water column up and initiating the tsunami. It's not like the tsunami is radiating from an epicenter as a pebble in a pond or something. Well, in the Cascadia case, the discoveries were hastened by questions surrounding this pair of power plants that were under construction in the early 1980s. The acronym stands for Washington Public Power Supply System. Many of you know it, but the acronym doesn't roll off the tongue very well, but when it does, it comes off as whoops. And whoops got it. The people running whoops got in over their heads and borrowed a lot of money they couldn't pay back. In the end, there was what was at the time the largest bond default in U.S. history. And they sought to recoup their losses some of their losses by completing the reactor vessel that's the nearer of the two reactor vessels in the photo, this one. And the Nuclear Regulatory Commission said, this is interesting. In the 1970s, when you considered these, when you designed these, that subduction zone wasn't thought to be an issue. But now the geophysicists tell us that it's an active fault, and though they don't know whether it makes very big earthquakes, maybe you should be thinking about this. So the NRC went to a USGS seismologist, Tom Heaton, who was among those who drew comparisons between the subduction zones and others, and he ended up with a double negative. I can't remember how he put it. It's something to the effect of, you can't conclude that it can't produce earthquakes, or very big earthquakes, because he couldn't show that it had done this, but that he could show that this subduction zone looked like subduction zones that have done it in historic times. And it was easy to think that the 200 years since Lewis and Clark wouldn't be enough. So that was that framed the question for geologists, coastal geologists like me, and so a bunch of us got into the act at that point, and portage was very much on our minds at that point, because that was up there as an example of how land dropping during an earthquake can kill off a forest. The the estuary can bring in silt and sand, mud, build up a pile of stuff, preserve some of the plants, the stumps of the trees. And we had these western red cedar that really preserved well. So this is where Cooper gets back into the act, though at the start, none of us knew about Cooper. So the best preserved of those ghost forests is one that Cooper never saw. It's a bit farther north from Willapa Bay. And these are standing out in a tide meadow along a stream called the Copalis River. There's Cooper, just his ghost up there. So that's just the most graphic of the evidence. Usually it was marsh grasses and stuff in the position of the trees. But the principle was the same, that vegetated low-lying places along the coast got dropped and essentially made into bare tide flats. And the mud built up on top, and the plant remains preserved, and you could see that the land had abruptly dropped. And that kind of work was done up and down the coast by scientists from Canada, a couple different research groups working in Washington, likewise in Oregon, and a group down in California. And one of the the work went on almost simultaneously in the late 80s and early 90s. And it was a kind of exciting thing. You'd go to an estuary that you hadn't looked at before, and you'd say, I wonder if I'm going to see evidence that the land abruptly dropped. Because there's an alternative, and it's what makes the land in the delta so low, and the Sacramento-San Joaquin Delta so low, right, is that the soils there are made of peat, great piles of peat that built up as marshes just kept their heads above seawater. They never got drowned like these ghost forests or anything like that. So you just have big piles of peat, and then it can oxidize and go away. So that would be the alternative. Were there at these estuaries places where you could see that marshes had managed to keep their heads above water steadily for thousands of years. And every estuary looked here had this evidence for abrupt lowering of land. And the safeguard, a further safeguard here, and it wasn't a bandwagon effect, was that you had these different research groups because they had they're very good incentives in science to show the other people have it wrong. So that was one thing. And then a really marvelous thing, too, was, as you saw, tsunamis are part and parcel with land level change because it's essentially a land level change under the ocean that's raising the column of water above it and initiating the tsunami. And so a land level change that lowers the coast probably extends underneath the adjacent seafloor as well. And so you drive a tsunami on shore, right? And we've seen that. So in this case, we'll start with a tide marsh. We'll drop it down. The tsunami will come in on the freshly down-dropped landscape, maybe knock the plants over slightly, and then the mud will build back up, and we'll have our geological record at right of the occurrence of the tsunami. So here's some school teachers, one in the red from Portland, and in the yellow from Vancouver, Washington, and they're on the banks of a tidal stream at the estuary where Cooper spent his time at Willapa Bay. And so the modern salt marsh surface is up here, and it's a very low tide, and so the tide is out of view here. And the bank has been cleaned off, and a nylon window screen has been tacked up, and then this water-loving glue has been painted on top. And it's a non-toxic kind of thing. And the glue, the hardener for this, it's a two-part glue, and the hardener, like a epoxy or something, the hardener is water. And so the glue really likes to penetrate wet sediment, which this is. And in the bank, the reason they've placed it here is you can see this dark stuff here and here. So that's the soil of a marsh that was there before the land dropped. And then above there are these little stripes, and these turn out to be layers of sand from tsunami. So peeled off, that's what it looks like. And so you can see the soil of the marsh, and then above it, 1, 2, 3, 4, 5 sand layers stand out in relief. Each of them probably represents a different wave in the tsunami wave train of the evening of 26 January 1700 by the Japanese dating that we'll get to. So, I mean, this stuff is out there, and it's really easy to see once you know to look for it. One thing about ways and means, a lot of this work is physical, and these shovels really make a difference. They're World War II shovels, and they have just the right balance, but your ability to observe depends on your ability to sculpt these outcrops. There's no excuse. The stuff is soft. You can cut into it. It's not like dealing with bedrock geology where you can't easily blast, to get what's underneath. But here you're really responsible for cleaning this stuff, and it makes a big difference to have simple tools like this that work. Okay, so here's another case of a tsunami overrunning something, but in this case it's more of interest to human beings. There were native peoples, of course, and they used those tidal streams, and they fished and all this stuff. In January 1700, they probably would have been inland, but by the time they got out to their fishing camps, whenever it was after that, they would have found them put out of commission, first by having been overrun by tsunami, but more importantly by having the tides come over the freshly lowered landscape. So we'll look at in the next view, we'll look at a right-hand frame that's down in Oregon. So the story, you read, that's a vertical bank, right? So you read this history just as if you were scraping into the floor and you're encountering progressively older layers of paint. And so the oldest layer of paint in this picture is the sand from dunes. And people set up shop on those dunes. And at this place, they were harvesting elk. And there were lots of elk bones. And let's see, this was true in California also or not? I don't know. In the Northwest, the ever-ready batteries were stones that people put in fire. And then that became the way that they could heat water. Or if they wanted to bend the sides of a canoe, they could put in the water for that purpose. Anyways, there are fire-cracked rocks in the pit. And then the sand that's probably from tsunami sits on top of that, and then the tides brought in the mud after that, okay? And put the fishing campsite or the elk campsite out of commission. Well, this led to something of a finding, but also a bit of an impasse, a quandary. This work that was done by these different, somewhat competing groups in British Columbia, Washington, Oregon, Northern California, they all found that they had this evidence of repeated land level change, of lowering of land, and they all found evidence for tsunamis coming ashore in association with these land level changes. But they couldn't figure out, none of us could figure out whether the whole fault had broken at once along its full length in the dinner sausage model at right, or whether, as cartooned at left, there had been a series of shorter breaks. So at left, you have 3 different earthquakes represented by those rupture patches, okay? And the shaded area, again, represents the area where on the fault projected to the surface on which the fault plane would have slipped. And these are just cartooned, but the idea is that over a period of hours or years or decades, that you could break the zone piecemeal. Okay? That's an alternative to breaking it all at once. And so how do you test those things geologically? You need a clock, right? Because you want to know, did the whole thing break in a matter of 5 minutes or so? Or did it take 2 days or 2 years or whatever? And so how do you date things exactly enough? So there are a number of props down here, but this one is from the initial dating exercise. It's from a spruce stump jutting out of a bank at Mad River Slough in Northern California, part of arm of Humboldt Bay. A coping saw piece has been taken out here. These are rings that formed 35 to 45 years before the last ring in the root. And then there's another piece we cut off on the outside. And this was part of a radiocarbon dating exercise that narrowed the time of tree death. And tree death is the signature of the earthquake, right? If the earthquake is accompanied by lowering of land, and the lowering of land kills the trees, then the signature in this tree of the earthquake is death. Okay? And so the problem was that, yeah, we were able to limit to between 1680 and 1720 the time of tree death for these trees at Humboldt Bay, and for some up in northern Oregon, and for some in southern Washington. Everything, all the spruce we tried this way came out with those sorts of ages. But it could have been either the breakfast link or dinner sausage model to explain it, because the clock wasn't exact enough, right? You could have had a series of earthquakes between 1680 and 1720, or a single big one. So this is where we got rescued by Japanese earthquake and tsunami historians. So one of these ended up working for MacArthur as the occupation forces. Before that, he had been a secondary school geography teacher. He wrote an English-Japanese dictionary. And he worked as a volunteer for the Earthquake Research Institute of the Imperial University of Tokyo, which after the war got rechristened the University of Tokyo. And his job as a volunteer was prompted by a disaster in the nation's capital, in Tokyo, labeled Edo here for its previous name, where in 1923 there were some 150,000 fatalities from the combination of earthquake and fire. And Musha was set to work to see if he could, in a way, to predict earthquakes by looking back in the past, and to mine the long written history of Japan going back into the 700s or 600s to do that. And so during the war, his project was coming close to completion. And by mimeograph, he issued his handwritten a collection, his anthology. The green volumes at right were issued during the war. And the title at top begins with a character that looks like a person with arms and legs, and that's the oki or dai or big character in Japanese, and it means that it's an imperial product. And then the post-war volume at left lacks that character when the imperial part goes away. And the volume at left was in manuscript form, preserved during the firebombing of Tokyo by being buried in a seismologist's backyard in a galvanized steel box 3 meters below the ground. So Musha collected 2 accounts of our tsunami from the Pacific Northwest of the United States. And one of them's up at number 3, and the other's down at number 6. And they are in that second volume that was a collection of stuff that this is a printed version of what was issued during the war in mimeograph. This helped out other Japanese earthquake and tsunami historians in 1960, when they were kind of reeling from the surprise. They knew that a very big earthquake, seismologists there knew that a very big earthquake had happened in Japan, in Chile rather, but they didn't expect that they would get damage in Japan from the tsunami. And so the first tsunami warning was issued only after the first wave was ashore. And at this place, Ofanato, there were 53 fatalities, and the experience prompted historically minded researchers to ask what find in Japanese archives about other floods from the sea that arrived without shaking or storm being felt in Japan. So think of the cat cartoon. The message there is if you feel the ground shake, a tsunami is coming. But the message here was, even if you don't feel the ground shake, maybe a tsunami is coming, right? And so they were curious about these other, and they had the Spanish language catalogs of earthquakes in South America. So they were able to match, and they knew that it's about a 24-hour travel time for a tsunami coming from the west coast of South America to Japan. So they could go to the archives from colonial Americas and add 24 hours essentially to the time of occurrence of the event down there, and then say, what do we have in our documents from that time? And they were able to identify all those. Plus, they had one in January 1700, and they didn't know where it came from. So this is one that Musha had already collected, but they added to the collection. And still further additions came from a group that did this in the 80s and 90s. Their exploration was prompted in part by student unrest that in the late 60s or early 70s, I don't have the dates down anymore, but there was a student takeover of the Earthquake Research Institute building at the University of Tokyo for 2 years. So unable to get to their research offices, some of the scientists involved there said, okay, well, we'll go out in the countryside and we'll collect records of old earthquakes and tsunamis. And so that effort partly sprang from that. Also, this work was as I understand it, was supported in part by TEPCO, the operators of Fukushima reactors. So there was interest in the Japanese electric power industry in doing this. The earliest known versions of accounts of a tsunami in January 1700 in Japan are the ones shown on this screen, and their places are plotted there on the map. The styles you can see are the writing styles are very, very different. The right-hand two are full of squash spider characters. These are the Chinese characters that a person in the kind of the ruling class, the military caste, the samurai, they were at this point in 1700. It had been practically 100 years since consolidation of power by the Tokugawa shogunate, and so it was a time of stability, and these people were working as bureaucrats essentially. And so but they knew their Chinese characters and they wrote them well. And then and so did some merchants. Numbers 3 and 6 are in the hands of merchants. The number 6 merchant was working as in a hereditary position as a mayor of the castle town of the cat cartoon. And number 4 is an account of what would you say? It's a police report, a traffic accident report, an insurance document concerning a boatload of rice that got held offshore all day by waves, strange waves coming in and out of a port. And then at night, a storm came up and it dashed the boat into the rocks, and all the rice was lost. And the local villagers were in a position of being accused of stealing things. So they went to the local samurai and then said, okay, write us something that clears us. And the ship captain probably needed an insurance document. So that's the origin of number 4. And so, I mean, they're sort of amazing. The numbers 1 and 2, number 1 reads like a FEMA document. It's just sort of amazing. And number 5 is the one we'll highlight here. It's from an involved, inquisitive, and slightly pretentious eyewitness. We don't know his name for sure. He's the village headman a village of some 300 people, 325 people, down on this pine-covered peninsula that commands a beautiful view across to Mount Fuji, shown here before it became asymmetrical with an eruption in 1707. And the road swinging left to right is the one that connected Imperial Kyoto to the shogun's headquarters in Edo in Tokyo. And the retirement villa of the founding Tokugawa shogun Ieyasu is the castle that you see there. This is part of a map. You see the source from at Berkeley, where Gilbert wanted to go, and the full. It's a strip map of the Tokaido, this highway, and at original scale, the map is 40 feet long. It's just an excerpt. So the village headman's accounts come down to us in a Best of the Beach Boys kind of presentation here. Somebody in the 1700s saw that there was historical stuff of interest and in the collection of documents that had been left by various headmen. And no doubt these had been ravaged by bookworms, literally, and maybe typhoon, fire, who knows what. And so they were copied out. So this is a secondary source. Some of the others are primary sources. This is a secondary historical source. The book is full of detail. One of my favorite one has to do with one of the two elephants that were sent to Japan, a male-female pair, by merchant from Korea. And in 1739, an elephant passes through a nearby village. This is just a summary. 7 years old, 2 meters high, 3 meters long, tail extends 1 meter, its tusks 4/10. These are written actually in Japanese units at the time. Its ears are shaped like ginkgo leaves, its eyes like leaves of bamboo. Its daily diet includes 100 tangerines, 3 gallons of cooked rice, and 5 gallons of sake. So the village these village headmen was, they were noting interesting things. So this is that same account, and this village headman does not know the Chinese characters that our FEMA friends in the north knew. And so you see this cursive look and these very simple characters. So some of you who read hiragana in Japanese can recognize some of the characters here. So I'll try to read an English translation of the main parts of this account. And it will be in a Japanese syntax where the preposition will follow its object, and the verb will tend to come at the end of the sentence. And we could use this as an index map if we wanted, but I think I'll go to this one. This is a closer view from a map, a 1702 map from the Tokugawa shogunate, and there's a shrine that's mentioned in the account. That this is Miho. Mi is in Japanese can be 3. And there's the number 3 in Japanese. So this is and there are, of course, the pine trees. So the account says, first he tells you when this is. 12th month, 9th day. Oh, this is also blue moon. So the year that this happened, the 12th year of Genroku era in Japan, was a leap year. And it was a lunar calendar. So they could not have blue moons in that calendar because the days were only, is that right? Yeah. Only 29.5 or days on average long. But this created a problem that every 3 years you needed to add a month to your your calendar in order to get it back in sync with the sun. And there were a whole bunch of rules about, the auspicious times to add the month. But anyways, this was the 12th month, really the last month. It was the 13th month if you really count them because they had an extra month, number 9, that they inserted beforehand. And so this is 12th month, which sounds like December, but in a Western calendar, it's January. 12th month, 9th day, morning hour of 6. The clock was divided into each 12 hours was divided into 6 somewhat uneven parts. And hour 6 happens to be in the morning, early morning hours. But the numbers go backwards, so we'll see. They'll say number 4, hour of 4. That's later than hour of 6. I don't know. A friend of mine took Japanese, and she said it cleared out the cobwebs in her head. So, all right. So wave, and then he gives some places. Water became high. High tide, or something like, entered within pine groves up to that far reach. So got somewhere into the pine groves, and he gives some place names that you can kind of locate today. And then when the water went out, he says, as for that, the big river of speed like. And then that day's hour of 4 until, I think he means that's about 10 a.m., 7 times about rose, gradually became calm. Noon after from sea quiet became. Okay. Never heard of waves of rising condition because of village old and young, shrine to escape. Okay, so he's probably a young Turk who can run fast, and he's telling a more senior person like me, you better go up to that shrine. Because in the previous September, there had been a typhoon with 2 fatalities here, and the village had taken refuge on the shrine, which was on the high ground. So they probably went to the shrine in the picture. Let's see. What does he say next? Okay. Now he gets inquisitive, and he affects, according to one of my Japanese co-workers, who was the granddaughter of a Tokugawa scribe. He affects an academic style and totally fails. But he likes to use something that's kind of the equivalent of et cetera. It's nado to, he says. And she thought it was hilarious. So he says, to the old asked, but unusual the waves' appearance, they said. So that the entire village was puzzled. Tsunami, then he says, tsunami nado to, suzunami nado to. Okay, so tsunami and such, or etc. And suzunami, which may mean wild waves, but nobody uses the term, and such. What is called such a thing could it be? So he's heard of this thing called tsunami, and it's great. He's seen the cat cartoon. You'll see. For many years to come, remember well must. Okay, here he goes. Furthermore, earthquake, nado, earthquake, etc. Earthquake and such happens if that reason, yotonami, we don't know what yotonami is, but nami is waves, so he's talking about this phenomenon. Yotonami and such are things that come, it is said, but this village vicinity in earthquake any did not happen. Yeah? Right? So this is that he expects the cat association and he doesn't get. So he's wondering, is this nonetheless the tsunami? And so for me as a person working, living west of I-5, I mean, it's a real marvel to read that and hear this person speaking to you from the other side of the ocean from 315 years ago, and in another culture, and asking where his tsunami came from, and you're living in the area where they probably came from. I mean, it's a remarkable thing to make that connection. So that connection was put into a computer by a fine Japanese geophysicist, Kenji Satake, who made this snapshot from a tsunami model. And if we showed the whole thing, you'd see it just, the tsunami progressively radiating westward across the Pacific. So this, of course, is just the opposite of what happened in March 2011 when a tsunami generated along the Japanese coast went over to North America. And the effects of the tsunami in March 2011 were great on the near-field coast, right? Because the waves were big and they arrived fast. And there was a little bit of loss of life and something like $50 million worth of damage on this side of the pond, but comparatively minor effects, right? And so now you're looking at the reverse of that. And so you're thinking, okay, so in that way, you can hold up what happened in Japan in 2011 as something of a mirror. But anyways, in the simulation, the tsunami comes down the coast. You see the Genroku 12 months. We've talked about that. Hour 9 is either midnight or noon. They say hour 9 at night. So that's how, and allowing for a 10-hour flight between SeaTac and Narita, which is tsunami speed, that's how the evening of 26 January 1700 was identified as the time of this otherwise prehistoric tsunami in northwestern North America. I mean, this might as well be back in the time of the dinosaurs in terms of dating, except that you have this kind of precision. But it really wasn't. It wasn't all that clear to those of us in North America. The radiocarbon dating that I mentioned, there was radon contamination in the lab that made these measurements. And the dates we got on them had 1700 at the lunatic fringe of possibilities. I was very skeptical of 1700 and encouraged Kenji Satake to reconsider even publishing his results. But the lab straightened out its radon problem, and 1700 fell into the time again of tree death. But still, that's a very broad window, right? January 1700, it's pretty easy to fit January 1700 somewhere between 1680 and 1720. So it's a very permissive fit. So how do you test it? You're never going to demonstrate that it was exactly the same time, but you could show if it was different. If you could show that, suppose you could show that these trees died in 1698 or that they had died in 1702, then that Japanese tsunami could not have come easily from this place. So that was the game of trying to improve the precision. So the characters in this, there are 4 estuaries. The northernmost yellow dot is the place I showed you with the trees sticking up out of the marsh. And the others, the southernmost is Columbia River, and the other, Wolf Bay, second down. But this is a good pointer. So this comes from one of these trees that was sitting up onto old-growth western red cedar. Weyerhaeuser cut this down in 1986, and the tree was standing up on a hill high enough that the tides could not reach it. So it's a witness to the crime, okay? And the exterior of the tree, there's bark out here, and then this is the rotted out interior, and there was another sort of the western red cedar has this glorious phenomenon called butt rot that rots out the middle. And there's a tree ring scientist who worked with these guys here, the victims, right? So let me advance the slide so you can see him. Okay, so his grandfather was sent to concentration camps in Idaho and Oklahoma during the war. And what David did was he measured up the rings in the Weyerhaeuser cut witness trees going back. These go back to 1439. And he had others that took him back farther. He built a master barcode of wide rings and narrow rings. He figured out a master barcode going back that far, okay? And then he measured the rings in the victim trees. And this one's got the weather-beaten exterior, okay? And then he asked whether the barcode in the piece of barcode in here fits at this place. And then he'd ask, does it fit here? Does it fit here? Does it fit here, right? And he'd compute a goodness of fit statistic for each of those places. And if he had enough rings, this one contained too few rings by far. But if he had enough rings, upwards of 200 or 300 rings in the victim tree, he was able to get a strong statistical match at just one place. So he knew the dates of the rings in the barcode, the master barcode, right? So then he could assign dates to the rings in the trunk wood. And then there's one more part of this. Gotta go back. Whoops, the other way. Okay, so here's where the shovel gets into action, because you've got to dig down to where the bark is still preserved on the roots if you want to ask a tree, when did you die? Because what we were asking these trees is, did you die just after January 1700? As Kenji Satake says you did. And so we had to dig down through about a meter of mud, and not all of them had it preserved, but here's an example of a root that has a very beautiful sapwood all around the outside. Before the chainsaw rattled it off, there was bark on the exterior. So it was possible to get out to the last year the tree was alive. And we were able to ask these trees then, you know, what is it? David had dated the trunk wood, and we could drag the date down into the roots because there are marker rings, certain rings that are characteristically narrow. So you could track those down into the root and then go out to the bark and ask, what is the year of the ring at the bark, right? And so in 7 of the 8 trees we're able to do that with, that ring was a complete ring from the year 1699. Yeah? And so the growing season goes maybe April or May to August or September, right? So these trees lived through September of 1699, and they were probably dead by May of 1700. And the Japanese tsunami is January. So with that kind of resolution, you see, we can't prove that this is January 1700 tree death, but we could have easily shown that it was some other time, right? So that's the way. I think they say fail to falsify is about the best you could do. Okay, so the punchline then became this. There are a couple of these signs that were dedicated just after the 2004 Indian Ocean disaster, but you know, this story came together in the 90s. Here you're on the part of the Oregon coast, and it's a memorial to the presumed victims, Native American victims of the 1700 tsunami, and it's also a tsunami education device, you know. So this is sort of the most direct way that people have used this story. And for me as a geologist, when I started working with seeing evidence for dead trees and buried soils and sand sheets and stuff like this, and I'd go out to the coast and I'd say, well, sometime between 1680 and 1720 there was an earthquake or a series of earthquakes, we don't know which, and you know, it could have been a magnitude 8 or maybe it was a magnitude 9. And so you're sort of always backtracking because you're trying to be honest about what you don't know. And now you go out there and you say, well, on the evening of the 26th January 1700, there was a magnitude 9 earthquake. People say, okay, they know what they're talking about. So that makes a difference in communicating hazard fundamentally, to have fewer uncertainties. Here's an example of a hazard communicated after the fact. So the sign went up here in Thailand after the 2004 Indian Ocean disaster. The sign was designed in Oregon in the, I think, late 90s or early 2000s. And so this is the kind of thing you want to get out there beforehand, right? And that's, in that sense, the history that we've just talked about is a warning system. I mean, people talk a lot about earthquake early warning systems and tsunami warning systems, but in some ways, the fundamental tsunami warning system is knowing that you've got the problem to begin with. And that wasn't the case here in the Reagan years, right? So in the case of Cascadia, this is a kind of a messy diagram, but what the idea here is that, remember the breakfast links and the dinner sausage. So over at right is a dinner sausage for 1700, and underneath next is the question as to whether it's going to be a dinner sausage or breakfast links, a series of lesser earthquakes. And then arrayed at left, and then there's a scale that just shows the length of the fault and the width of the rupture, and the width is approximately scaled just as we had on the maps before. But in southwest Japan, there's a subduction zone that had a very, very big earthquake in 1707, and it broke piecemeal, 32 hours apart in 1854. So that's why we couldn't, even with the tree ring dating that David did, you couldn't tell, you know, something 32 hours apart with that kind of clock. And then in the 40s, 1944 and 1946, there were these pair of earthquakes. So this subduction zone is versatile. It can break all at once, or it can do the dinner sausage, or it's got options on its menu. And a classic example also off of northern South America there, with the 1906 Colombia, Ecuador, and then the series of earthquakes that followed. And then finally, the 2004 Indian Ocean disaster was spawned by a very long rupture, but there were some predecessors that were much shorter. So this is one of the big open questions with Cascadia. It's commonly said that Cascadia dependably produces earthquakes of magnitude 9, but I think that's without the supporting evidence from Japan, essentially, it's hard to make that case. The Japanese evidence was explained by, it's very hard to explain the flooding and damage in Japan by moving the amount of water that you'd move with during a magnitude 8 earthquake. You need a much bigger area of displacement to do that, according to the tsunami people. As for repetition, I know there's some estimates out there. They were cited in that New Yorker article about how about 250 years on average between big Cascadia earthquakes. The consensus numbers, at least for the strong evidence involving land level change up and down the coast, is close to 500 years. And the 250 is an estimate from offshore evidence that where those findings have not been replicated onshore. And it's from a single research group. So the safeguards that were built into the coastal work haven't been played out there yet. So I tend to go conservative, as it were, with that 500 round number. But this cartoon really represents a 3,500-year earthquake history inferred from land level change at those southwest Washington estuaries. And the yellow bars, if the yellow bar is really wide, it means I didn't do my job very well. And if it's really narrow, then the uncertainties are small. And the rings in the victim red cedars are showing their lifespans when the land probably did not drop during their watch. But anyways, you can see that the earthquakes happen like clockwork, and they're predictable, right? No, I mean, they're very, very, very irregular lengths of time between them, but there are some examples, like between about the year 400 AD and 700 AD, there's an interval of just about 300 years, 350 years between those back-to-back earthquakes. So in that sense, you know, you have precedent for short intervals. But then the preceding interval looks like it lasted 1,000 years. All right, so what are people doing with this information? There's a lot of effort underway, as there is down here, to protect people against earthquakes. And while the hazards that are out there are much bigger than the efforts to deal with them, it's still important to, I think, for us as humans, just to call attention to things that we're trying to do. It's sort of the glass half full attitude, I guess. But in this case, we're out on the Washington coast. Grays Harbor is near the Whoops plant. And the Pacific Ocean in the air photo is down at the bottom. And what you have is a school ground with the dog-legged dotted line pointing to an old circular gymnasium. So the air photo was taken in 1977. And the construction photo at left is of a vertical evacuation structure that's being built on top of, as part of a school reconstruction. And down below is an artist's conception of what the school gymnasium will look like. And you can see in the construction photo there are towers that are the towers that are on the corners here. And the entry will be here. And then there's to be room for up to 1,000 people on the roof. And the impetus for this came locally. There was a bond measure passed. I think there were 1,500 ballots cast for a local school district in this not very affluent part of the Washington coast in April of 2013. And by a margin of 70% to 30%, the bond measure went forward. It is something like $13.8 million that they're borrowing to rebuild this school. They knew they needed to fix the school anyways, and on the sort of the time scale of the tsunami warning provided by Earth history, they had the option of doing this, and they decided to do it. One of the things they did beforehand was to get some tsunami modelers to go out and figure out what kind of inundation they could expect there with an unusually large tsunami generated nearby. So the first part of it was just to figure out the lay of the land. So there's a topographic profile going across the kilometer scale. So if you go from the ocean to the harbor, it's essentially a mile. And the highest ground along this is about 20 feet, something like that, the tops of the sand ridges. And the schools, you see where they are. And so what the modelers did first is they say, OK, during the earthquake, what's going to happen? Okay? So they're not thinking of the direction that Maria Graham saw it. They're thinking, or George Klafker measured there out at Montague Island. They're looking at the portage direction because they know from the geology here that during the most dependable signature of big earthquakes here is land dropping, and that the amount of down drop can be on the order of 5 feet, something like that. So they assumed a better than 6 foot, 2 meter drop. So that's the first thing that happens, and it lowers the coastal plain that you see there in the air photo. And then they let the simulated tsunami come ashore. And what's plotted for the tsunami is the peak height attained. It's not that the tsunami looks like this in a snapshot view, but the peak height attained. And so they're getting maybe a peak height at the coast of about 35 feet. Above the post-earthquake high water level, and then the tsunami loses steam as it goes across the plain, and those two tall ridges, which the modelers allowed to be decapitated slightly by the tsunami, those two tall ridges still provide some measure of protection. So the water's only 1 or 2 meters deep at the site of the refuge. And as you saw, the plan is to have the top of that platform for 1,000 people be 30 feet above ground surface. So that's the top of the green bar on that graph. So you see the measure of safety they've tried to provide. And then they've built into the design resistance to strong shaking, and they're driving piles as much as 50 feet deep to prevent the building from being undermined by tsunami scour. And for that, they're using some lessons from the 2011 Tohoku tsunami. So yeah, this is, there's a lot more of this that needs to be done, but this is where this basic research that goes all the way back, and you can see the Alaskan imprint in here in a way. I mean, the foundation from the studies in Alaska, and even going back farther to make it possible to have the scientific understanding to yield this sort of engineering design. Thank you very much.
Thank you, Brian. It's a little late, I know. But I know many of you have questions, and you already know the drill, some of you. We have 2 microphones in the room, one microphone over on this aisle and the other on the far side of the room. If you would, please get up and line up behind the microphones to ask any questions. Not only so that those of us in the room can hear you, but there are people watching online, and we want them to be able to hear you as well. So if you're not able to get up to come to the microphone, just give me a wave and I'll bring a microphone to you. So who wants to ask the first question?
We may have a victim there.
Go ahead. Mike, can you turn up this mic?
All right. Now you can hear me, hopefully. Yeah, thank you. This was a great talk. I really learned a lot and enjoyed it. I understand there was a seismology conference in progress in Tokyo in 2011 during the earthquake. Were you at that conference?
No, I've not worked in Japan since maybe 2005.
And so I was wondering if you would have liked to have been there, or maybe are a little envious of the seismologists that were there.
No, I don't think so. No, and it's not a matter of personal safety. It's this, that that's a whole nother talk of the Japanese efforts to understand the earthquake and tsunami hazards along the Japan Trench, and how those efforts were overtaken by the 2011 earthquake and tsunami. And some of this story has to do with scientific ideas that were just so deeply embedded it was hard to get past them, but people were making progress in that direction. Another part of the story is that in the aftermath of the 2004 disaster on Indian Ocean shores, the A-teams of many Japanese research institutes went to Indian Ocean shores partly in their version of USAID, JICA. And they provided a great deal more assistance than our country was able to provide, by and large, in those areas. And so in some respects, you could say that they were distracted from the hazard in their front yard. But Japanese researchers were very busy doing this stuff. And one of them, a paleontologist, a micropaleontologist I'd worked with a young family. Some of us wrote him just after the 2011 earthquake and tsunami, and we said, "Are you okay?" And we knew that about Fukushima, and they were close to Fukushima. And we said, "You know, do you want your family to come to the States? We'll be glad to take care of them," and that kind of stuff. And he said, "No, my family's okay, but my Jogan work is not published, and now it's too late." And Jogan was the name. Jogan's an era like Genroku. And Jogan is in 869, there was a predecessor to the 2011 disaster. And it was the job of geologists and paleontologists to figure out that disaster. And in the wake of the 2004 Indian Ocean disaster, they really went after that. But they weren't quite there, and they didn't get to notify people. So, you know, my reaction would be that from my part of the job of forewarning, that is the reaction of my Japanese colleague, that it's too late.
Yeah. Okay, thank you very much.
Okay, I have a question about, you talked about shoreline along the Pacific coast directly. How much hazard is there to Seattle and Tacoma on Puget Sound? Are they sufficiently shielded from the things coming across the Pacific and the Sound there, or will there still be water rising to certain significant heights? Okay. I got a cousin living near Tacoma. That's the reason I asked.
So the question was, what about the hazard from in the inland waters of Washington State? And you could even extend that to a question of what about the hazard in the San Francisco Bay?
Yeah.
Right? So you know the 1964 Alaska tsunami caused quite a bit of damage inside San Francisco Bay. And it was a case of strong currents. It wasn't high water, it was strong currents. And I think a lot of the damages was in Marin County. That's certainly a hazard at Puget Sound. There are other hazards as well. Perhaps the biggest one is that shaking from a prolonged earthquake like this with the bluffs of Puget Sound could cause some of them to fail. Or with the delta fronts, the Puyallup River, the Duwamish, the ones that head it, or for that matter, the Skagit, the ones that head on the Cascade volcanoes, they have built these deltas out. And the experience in Alaska in 1964 was that delta front failures were responsible for the main for a lot of the fatalities from tsunami in Alaska. And there was, with 64 Alaska, it's truly the plural tsunamis, because you had the open ocean tsunami with a tectonic source of raising the seafloor and stuff. But then you had these slide-induced tsunamis, okay? And so slide-induced tsunamis would also be a concern at Puget Sound, and they would be fast arriving, right? For a tsunami generated off the Pacific coast of Washington to get to Seattle or Portland is a matter of probably an hour and a half or more. But for the shaking to set off a slide in Puget Sound can give you the tsunami inside Puget Sound very quickly.
So is Portland at a hazard on short notice after a major quake?
So in the case of Portland, there's my impression from the geologists and engineers in Portland is that they worry a lot about ground failures that cause damage to important facilities, be they oil tank farms or bridges, things like that in Portland. The Columbia River actually is the site of the one known historical tsunami fatality in the state of Washington. And this was a result, probably, some say, of highway construction on the Oregon side in February, or maybe just freeze-thaw in cliffs of Columbia River basalt that crashed down one night into a deep part of the Columbia. And the wall of water went over a levee, kind of like out in the Delta or something, and crashed into a couple of houses, and one life was taken. So you know that it is possible on certain stretches of the Columbia to have local waves made, but in Portland that might be difficult.
Okay.
Yes, this is for my personal well-being. I want to know this. Okay. I came from Sacramento because I really wanted to ask you this question. I am a teacher.
Uh-oh, I read, you play billiards?
No. And I love the North Coast, okay? I love the North Coast. Oh, there's George. I liked your thing, your lecture. So when I went to, when I go up there, I pass all these signs, you know, where you're going down the North Coast, and it's like, leaving tsunami, entering tsunami. And I'm like, it seems so low, because I look at those pictures of the Tohoku earthquake, and I'm like, oh my gosh. And when you talk to people that live on the coast, they're like, oh, no, it won't hit here. And you're thinking, right. You know, and so my question is, are those signs, would you trust those signs?
I know the history of, some of the history of the signs in Washington State. Some of those signs were put up before tsunami inundation maps could be made. And it was the decision of, and I think a good one, by not an emergency manager, so it's just me speaking as an individual. I don't know anything about this topic, but that the emergency manager was prudent to at least alert people that there was a hazard, and she put them in places that were obviously vulnerable. And then the maps came along, and as you know, for the Crescent City area, there are tsunami evacuation maps that have been prepared. And maybe they're on their second generation of them, I'm not sure. Oregon is on its second generation of maps, so is Washington State. And these maps help you to identify what places are vulnerable, and they point you to places you can get to high ground. The new map for Westport here anticipates the completion of the refuge structure, and it plots that structure on the map.
Okay, so that's good.
You know, so I mean, they're doing that. They're trying very hard to do this kind of stuff.
Okay, and then if it's okay.
Yeah.
The tsunami that hit Tohoku, when it came here, we all watched it on TV, you know, and it didn't look that serious. The boats rocked up and down. But it sounds like the one that came from the Cascadia and that hit in Japan was worse.
I don't know. You saw the village headman said high tide or something like. Tsunami, could it be? You know? And,
yeah.
And if you read the other accounts, you can get this online. It's a USGS book, Orphan Tsunami of 1700, and all those translations are in here. And you'll see that only one of the accounts refers to it as a tsunami. In only one of the accounts is there appreciable damage. 20 houses, was it 20 houses? I can't remember. There are a total of 33 houses, and some of them are burned, and others are actually destroyed outright by the waves. And that became one of the clues to figure out the size of the tsunami. But that's the only place where housing damage has actually been reported in Japan, and from our tsunami. So it really is a diminutive version of what was you know, overrunning that elk processing plant along the Salmon River in Oregon, for instance.
And one more. I live in Sacramento, and they keep saying that if the Cascadian Fault ruptured, that it would impact Sacramento, and I just, it's awful far away.
What you can do with that is you can go to the National Seismic Hazard Maps, and I think you have to go back one edition to the 2008 versions, and look for something they call deaggregation. And you can click on Sacramento or enter the zip code, and you'll get displayed a graph that shows earthquake size on one axis and distance from the fault on a second axis, and earthquake and contribution to the hazard on the on the sticking up. It's a 3D graph, kind of a perspective thing. It's pretty cool because you can ask what the faraway Cascadia subduction zone contributes to the hazard in Sacramento. And my understanding is from the 2000 and the generation of maps before that, I guess it would be 2002, that at the time they made those maps that the Cascadia zone was the single largest contributor to hazard to buildings of 10 stories or greater as far south as Sacramento. in the Sacramento Valley. Now, whether that still holds with the 2008 maps, you can check for yourself, because those sorts of estimates change.
Thank you.
Yeah.
Hi. On one of your slides a while back, you had a map of the Puget Sound area with a bunch of dots for where dead trees had been found. And I noticed one of them was on the eastern side of the Puget Sound. I was wondering if there had been other areas on the eastern side of the Puget Sound within the sound where we'd found that the ground had lowered. And
yeah,
it's going to be a lot of slides back. It was the first
we can
half
find
hour or so. But just curious as to...
It's that one, right?
Yeah, just curious as to if there's been any others on the eastern side of it, and what that tells us.
There's a really good bakery down here. It's called the Blue Heron. And they just moved from the low ground up to high ground. But the Blue Heron right next to it has a red cedar snag. And it's got some spruce roots in growth position. And the dating that's been done there so far is quite permissive compared with the dating of these red cedars out here, but it's consistent with lowering of land there. So that, if so, that's as far inland here. But recall the maps of Alaska with the huge swaths of lowering. And it's a great big broad downwarp, and it wouldn't be surprising to see it coming in there. So there have been some other efforts to look into inland effects, and this is an important thing. People try to learn about how close to the urban areas does the fault break. So the fault is slanting underneath the area of the arrow here, right? And Seattle and Tacoma and Portland like this. So they're inland of the part where the fault breaks. And how far inland are they? Because the closer they are, the greater the ground shaking that's expected. So this is one of the open questions right now with Cascadia, is in making these sorts of hazard maps, is that aspect of the proximity to the fault.
So would we have any idea if, like, for example, had it fallen, let's say, from 1 foot above sea level to 1 foot below, there wouldn't even need to have been a wave per se, right?
I'm sorry, I didn't get the last part. There wouldn't be
if the land where those dead trees are had been 1 foot above sea level and then fell to 1 foot below, you wouldn't need a wave necessarily. Do we have any idea of knowing about that?
Okay. So the evidence, this is independent of tsunami, completely independent of tsunami. There was no, I don't think there was a tsunami at Portage, okay, but the trees died. So it's the long-lasting effect of the relentless attack of the tides that does this, okay? And so it's easy to get confused and think that trees like this are victims of tsunami. They were probably overrun by, there's this comes from about here, and there's the buried soil. There's the sand sheet, and there's the tide flat mud above. I mean, it's the 1700, and there's a mud layer here and a mud layer here. There were probably at least 3 waves represented in this. So it's the 1700 tsunami almost certainly, got in there. But I don't think it's responsible for the deaths of the trees in January. Probably, unless it was a really dry year, they had enough rain to rinse the salts out.
Okay, thank you.
Yeah.
Let's take one final question. It's getting late, and go ahead with your question.
I'm the last one, I guess. I was wondering whether there's any concern or any activity going on relative to the tons of radioactive material that's buried at Hanford.
At Hanford. There's a lot of research into faults and folds over in that part of Washington State. And related to that is research on faults and folds that may affect dams along the Yakima River and its tributaries. And there are big water supply systems for farms and whatnot over there. So Bureau of Reclamation is supporting some of that work. There's long-standing interest in finding that out. It's not very easy work, but they are identifying evidence for faulting since the Missoula floods, the Ice Age floods, on some of the surface rupture on some of the faults that are in the Yakima Fold and Thrust Belt, which is near Hanford. So, yeah, there are efforts to assess the seismic hazard. I don't know how that, how that relates to the engineering of the for the waste that's stored over there.
Thank you. It was a very interesting talk.
Thank you.